But I want to welcome each one of you who are joining us over Zoom for this Lunch and Learn with Dr. Leigh Stearns. I'm Ruth Rosal, Director of the Buttrey Center here at Central Seminary, and really delighted that you have chosen to join us. We are also delighted to have Dr. Stearns with us today to tell us a little bit about her work as a climate scientist and what she sees as happening that concerns her, and more about causes and impacts of climate change and what we all should be doing about it. It's kind of a big order for one session, but I'm sure there'll be some really good points that we'll be able to learn from her. She will speak for about 40 minutes, I think, around that amount of time, and then there'll be an opportunity for you to ask questions that you may have been wondering about in regard to climate science that undergirds our understanding of climate change. So you can write those questions in the Q&A, and the Q&A is actually under the More button on your screen. At least that's where I found it. If you can't find it there, then you can put it in the chat, but Q&A helps us to locate those more easily. And then, or you can wait until the end of the session after Dr. Stearns has talked and be able to unmute and ask those questions yourself. During the presentation, I do encourage everyone to keep muted so that both for consideration of others and because we are recording the session. And then also that you refrain from chatting or very much chatting on the chat so that you can pay attention to what is being said. Dr. Leigh Stearns has a PhD from the Department of Earth and Climate Scientists at the University of Maine. She is currently a professor in the Department of Earth and Environmental Science at the University of Pennsylvania. Previously, she was an associate professor at the University of Kansas between 2009 and 2024, during which time she attended Plymouth Congregational Church in Lawrence, Kansas. Her research specializes in studying glaciers, their changes, and the effects in both Greenland and Antarctica, and has a substantial number of publications related to this. We are also very fortunate that she is interested in climate education and literacy for all ages, and so has agreed to be the seminary's climate scientist advisor through the Climate Science in Theological Education grant we received from the Dialogue of Science, Ethics, and Religion project. And so we're grateful that she can speak with us today. So we welcome you, Dr. Stearns, and we look forward to what you have to share with us.
Great. Well, thank you so much. I'm really honored to be invited to give this little lecture, and I hope you learn what you hope you want to learn. All your questions about climate science. 40 minutes isn't a lot of time, so write down my email there on the bottom, or you can get it from Ruth later if I don't get to your burning question today. But I appreciate you taking the time to learn about this issue. As Ruth said, I was at the University of Kansas for 15 years, but I was born in New York City, going to St. James Episcopal Church. Then I went to college in Minnesota, where I maybe went to the college church a little bit, but not a ton, I hate to admit. The Ohio State University, where I went to Trinity, University of Maine, where there's a small Episcopal church also called St. James. And then in Kansas, where I was for 15 years, I attended Plymouth Congregational Church, and I moved over the summer to the University of Pennsylvania. I was in Kansas for about 15 years, finding my home church here. So just the different places and the different locations that I've been. Today, I want to talk a little bit about my research, kind of overview of how climate is changing, my perspective of why I'm concerned, where I'm concerned, a little overview of what my particular research is about, and then what we can do about it and how this is so interconnected with a lot of things that you all talk about and think about daily. So hopefully that is what you have come to learn. So just to start off with an overview, we know that climate has changed throughout geologic time, throughout Earth's history, and this graph here is kind of putting a little bit of that into perspective. So 0 is present day, And then the 20 is 20,000 years ago. So 20,000 years ago, when we were about 4 to 5 degrees Celsius colder, because these numbers don't mean that much, we had an ice sheet over us, over parts of the northern parts. Well, this ice sheet didn't quite touch Kansas, but over Pennsylvania, over New York. And we are kind of advocating as climate scientists, climate advocates, to stay below about 2 degrees, 2 to 3 degrees Celsius by 2100. So the numbers, while 3 to 4 to 5 degrees colder doesn't sound that much, or 2 degrees warmer doesn't sound that much, those are big changes in our Earth systems and kind of correspond to large changes in ecosystems and where ice is. The last time we were 2 to 3 degrees warmer than today, our sea level was about 80 feet higher during our last interglacial period. So these numbers kind of have large consequences for Earth systems. But we know it's changed in the past. And just to kind of put it, this 20,000 years in longer term perspective, this is kind of a crazy figure, but here's the last 20,000 years. So 20,000 years ago, we had an ice age. Every time there's like this double line means the time scale changes, which is a little bit confusing, but I think this illustrates the point very well. We have warm periods and cold periods, and these are our ice ages and our interglacials. We know these very well. We've mapped them in ice cores and sediment cores, a lot of tree rings, a lot of data goes into these estimates of how temperature has changed in the past. And we know we've had these dramatic swings in the past. And then if we go back, stepping 1 million years at a time, about 7 million years ago was a lot warmer. We had very warm time periods where, temperature was 12 degrees, 14 degrees warmer Celsius than it is today. And then very large swings, millions and millions of years ago. This is dinosaur time period. This KT extension is the extinction of dinosaurs. So in the past, throughout this long period of time, the planet takes about 5,000 years to warm 5 degrees Celsius. So we can figure out that rate of change from these old records. What we're showing now is that we can create a similar amount of warming in about 100 years and less than 100 years. And so that is a large part of the concern. A lot of people say, well, it was warmer in the past. Yeah, it was warmer in the past, but we had, crocodiles in Greenland and marsupials in Antarctica. So with these changes, the Earth can adjust to these changes. Species and society do not adjust to these large temperature swings, particularly when they happen really fast. So there's a little overview about kind of climate through geologic time. And throughout this time, we know that temperature and carbon dioxide in our atmosphere has changed hand in hand. When carbon dioxide is high in the atmosphere, the temperatures are warm. During the ice ages, less carbon dioxide in the atmosphere and colder time periods. So to look at kind of more recent changes, these are kind of averaged in the 5 years that you see up here, and just showing when it was cooler than at this baseline period and when it was warmer. So the yellow and reds show times when it was warmer. And a lot during this time period, you see pockets of warming, pockets of cooling. And then in the more recent years, you really see that warming is everywhere. And that's part of how we know that this warming is different in kind of natural cycles or oscillations like El Nino and La Nina. If the warming we're seeing is just driven by that, it would be cooler in one spot and warmer in another, or the land would be warmer, but the oceans would be cooler. And the fact that we're seeing such homogeneous, not homogeneous in terms of the patterns, but everywhere is temperature increasing, shows us that this is kind of a different beast that we're dealing with. One other thing to note in a map like this is that it's not equal warming. Some areas experience a lot more warming than other areas. And this plays into a lot of the inequities that we see in how climate change is exacerbated kind of throughout our society. But we'll stick to another figure of how the changes are presenting. This is I just think the schematic that they do at NASA is kind of cool. It's showing temperatures by month for each year on the left. And so you can kind of see how that's changed over time. And it puts in perspective how every month that we're seeing pretty much every year has been progressively warmer. And so it's not just that it's the winters that are getting more mild or the summers that are getting hotter, but we're seeing this kind of consistent shift. And what that means, kind of how it feels, is different based on where we live and what our job is or what we value the most. A heat wave, increasing it from, we're on path to reach a degree and a half of warming. In fact, we might have crossed it already. Whether it's 2 degrees, that's another almost half a month of heat waves. And so that's, a different need for air conditioning if you have that option, or places that don't have air conditioning. That's a lot of, heat related injuries. If we're thinking about crops, a little bit of globally average warming, which is what these represent, can mean a lot for where crops grow and how they grow. Another point I wanted to make with this warming, as I said earlier, is that those changes are uneven. If you noticed in that earlier plot, and this again is showing kind of where the warming is concentrated, is that it's really concentrated in the Arctic and in northern regions. And that's because the cryosphere, the ice sphere, is very sensitive. Ice and snow are very sensitive to warming temperatures. And we're seeing in the Arctic a lot of decrease in how much snow is on land and how much sea ice is in the ocean. And so the change that we're seeing in that feature of very bright reflective land masses that are replaced by either dark ocean or dark land causes this positive feedback of it's warmer, then the snow is melting, and then it's absorbing more radiation, and that gets warmer and warmer and warmer. And so the places that are warming the most right now are these areas that have a lot of snow and ice. Antarctica is not quite, the sea ice concentration is a little bit different. It doesn't hold on to sea ice in the summer, so every year is kind of a different beast. Whereas the Arctic, we have multi-year ice that doesn't melt in the summer, which is why the change is kind of exacerbated there. So the changes are uneven. When we talk about like a 1 degree temperature change, that is averaged over the whole world over one entire year. So in reality, that means that the Arctic might change or is changing 6 degrees, and Kansas is changing 1 degree, and South America might not be changing at all. So the distribution of that change globally is very different. And so how it's expressed for local communities feels very different. The next point that I wanted to make is that some of these changes are also unseen. We tend to think of global warming and temperature change on land because we live on land. We do not live in the ocean. But if we were sharks, we would talk more about how the ocean temperatures are changing more. And the ocean is absorbing, way more heat. In fact, 90% of the warming that's happened over the past 50 years is taken up by the ocean. It circulates, so it can bring some of that to depth. But a lot of when we think the land is heating a lot, the ocean is heating up even more. That expresses itself in many different ways, can cause more extreme weather like hurricanes and cyclones, impact sea level rise because of expansion of the ocean. When the oceans are warmer, they expand more, and that impacts sea level rise, also impacts glaciers and ice sheets. And as ocean water gets warmer, it doesn't absorb as much carbon dioxide. And so right now the oceans take up about a quarter of our greenhouse gas emissions. In a warming climate, they'll have less ability to absorb carbon dioxide. And so there are all these kind of feedbacks that are connected here. The next point is that 1 to 2 degrees, as I said earlier, that's a big deal. So that's averaged globally and annually. There's this cool interface or interactive website where you can put in what your town is, and it'll say, okay, well, according to this warming scenario, your town in 60 years will feel like, this town outside of Dallas. So, Kansas City is expected to be warmer and drier and higher emission scenarios in the summer, and warmer and wetter in the winter. So that will feel more like we're in Central Texas. which I think kind of helps, put some place to what these sometimes abstract changes might actually feel like. The other thing is we tend to think of climate change in terms of temperature because it's the easiest thing to have a direct relationship between carbon dioxide and temperature. We know that relationship really well. Temperature is just an easier metric to communicate and to model in our numerical models. But precipitation is probably felt more when we have droughts and when we have floods. Those are huge disturbances to societies. And in Kansas, the projection is that we'll be in the dry areas will get drier and the wet areas will get wetter. So if it's blue, it's expected to get wetter, and if it's brown, it's expected to get drier. So in the areas where we don't need it to get drier, it gets drier. And again, these are averaged over a year, so really does mean that more kind of higher precipitation events come all at once, not nicely spread throughout the growing season, but that they happen in these extreme events. Whether you're concerned about farming or water resources or the health of vegetation or rivers, these changes will impact those things that we care a lot about. The next point is that everything's connected. If we have changes in sea surface temperature, that impacts, the number of intensity of storms, and ocean temperatures impact sea level and air temperature and rainfall patterns. And so it's hard to think of anything in isolation because they are all connected. And we know that climate is really changing because we are witnessing it in all these different physical systems. There's not really one metric that we look at that does not have this fingerprint of kind of rapid change imprinted on it. So, just like so many things, everything's connected. And the last point I want to make, I think this might be the last point, is that we know how climate changes very well, and we have known for a while. So we have these, kind of extraterrestrial factors, how the sun is changing, Earth-sun geometry play a big role in pacing our ice ages. We know about greenhouse gases and atmospheric reflectivity from clouds. We know how the land and replacing sea ice with open water, or replacing grasslands with farmlands, or forests with grasslands changes kind of our carbon dioxide uptake and changes our climate. We also know about tectonic tectonic factors, including volcanoes and where the continents are. And in fact, a lot of these were developed a long time ago. And if you look at some of these old models, they match our current observations very well. The only thing they don't get right is our emission scenarios. And even Exxon, they had a publication in the 70s where they projected future temperatures based on emissions, and they have been pretty spot on. So even those who you might think would not understand or not want to embrace the relationship between greenhouse gases and temperature have known the physics of it for a long time. So these things are not really, these aspects are not under debate. We know it's not a natural cycle for several reasons. The one of the main ones is that we're seeing this consistent warming everywhere. And for a while, maybe 50 years ago, people thought, well, maybe it's like some oscillation we don't understand or we can't model well. If it was some kind of El Nino type of pacing or some natural variability, we would see different response from what the atmosphere is doing than what the ocean is doing. The fact that they're both warming is pushing us out of that kind of natural variability mode. We're seeing this warming exacerbate everywhere. And we also, because these brilliant scientists from 100 years ago up till today have been modeling this and have been kind of putting better constraints and uncertainties on all of these variables. So in this figure, the black line are our observations from satellite data, from weather stations that we have all around the world, kind of like, smush all that data together to come up with this black line of how temperature has changed since the 1850s. We know roughly what our aerosols, which act to cool the planet. They're kind of like volcanoes in that sense. Natural causes are here in green. So those are like volcanoes and, lands and ocean exchanges. And we can't get, so if climate was forced just by natural causes or just by aerosols, you get cooling, or just by greenhouse gases, you get this red line. You have to put them all together to have our observations match our model. And that's what these gray shadings are like. So, 20, maybe where are we now? 50 years ago or so, the signal, separating that signal and noise was a little bit more complicated. But now they're so divorced from each other, the natural causes versus the changes that we're seeing now, that there's no question that the warming we're seeing now is caused from a combination of human and natural causes. If it was just orbital dynamics and things like that, we should be entering an ice age in the next, 40,000 years or something. We should be actually cooling, but we're clearly not. So that's a little bit about the background of the science. Talk a little bit about my research now, which has been focused on this cryosphere, the ice, how is ice changing? And when I started, it wasn't really, I guess I was interested in it mostly because I liked glaciers and I liked being in these alpine regions and studying how they changed. The question of global warming and how they were changing dramatically was not part of the research. It was just kind of like fundamental change. And so I study how ice sheets are changing, how they're contributing more to sea level rise, how mountain glaciers, particularly in high mountain Asia, are changing and kind of impacting the distribution of water resources. And then I've gotten into the kind of study of sea ice and icebergs and how that's impacting Arctic navigation a little bit more. And so this video of Greenland shows, it's going to lighten up in a second with all these colors that show how ice moves from the center of the ice sheet out to the oceans in these glaciers. So it's just kind of like if you took a block of silly putty and put it on your table, it would kind of ooze out and deform under its own weight. Ice behaves the same way. It kind of flows in this way, and it flows faster when the slopes are steeper or the bed is lubricated. And that happens towards the margins of the ice sheet. But what's really fascinating is that neighboring glaciers do different things year to year. One will move faster than the year before, and the other will move slower, or one will retreat dramatically. And I'm really interested in understanding that variability and understanding what's kind of normal variability for a glacier and what's new. And the fact that we can measure things so much better now informs us a lot about the processes of how glaciers are changing and how they might change in the future to contribute to sea level rise. So sea level rise is the big question when we think about ice sheets and how they're changing. This is showing sea level contribution relative to 1900. From a large part of this is from melting of Greenland and Antarctica. And these are just different warming scenarios. So SSP 5, 8.5 is the very fossil fuel dependent scenario of carbon emissions in our atmosphere. That would contribute, almost a meter to sea level rise by 2100. Whereas if we are aggressively curbing our emissions, that's reduced to half a meter. But then you've got this like crazy line here, which is very hard to plan for. That is if like not all of Greenland, but if certain glaciers in Greenland or Antarctica underwent some large-scale tipping point or catastrophic collapse. And you might have read about the Doomsday Glacier in Antarctica that people are worried might undergo this rapid change. These changes have happened in the past. So when we look through the record of past climate, we do see times when ice sheets change, contribute a lot of fresh water really suddenly. And so we know this happens in the past. And the question is, are these things likely to happen now? And that's part of what's informing my work. Are these changes driven by ocean changes or atmospheric changes? Here's a picture of a map of Greenland showing the ocean currents that come around. One of the first questions that we're looking at is, does warm water, so one of the hypotheses is that warm water, since the ocean is a lot warmer now, is that warm water kind of eating away at the front of these glaciers. And this warm current comes up from the tropics and kind of wraps around south of Iceland, and it can bring warm water around the southern part of Greenland. If that's driving most of the changes, and most of the changes that we've seen of big glaciers are in the southern part, or is it from atmospheric changes that the ice is just melting more, and that's what's causing the glacier and ice sheet to change very dramatically? And the atmosphere doesn't have these kinds of confined currents. If it's warming, it could warm. There's no wall to like block that warming from reaching the top of Greenland. And so we expect different sea level rise contributions based on whether the ice sheet is responding more to ocean or more to the atmosphere. And you might think that's like it should be a very basic question or simple question to ask or to answer. But the surface of the moon is mapped better than the polar regions. And so, there are a lot of areas where we just don't know how deep the ocean is or what these fjords really look like. So I, in my research, use as much data as I can get my hands on. I use satellite data. I use airborne data to get at the bed topography of what the ice sheet looks like. I use instrumentation that is on the rock overlooking a glacier. I use GPS we put out on a glacier, and weather stations. And I work with oceanographers who use a lot of moorings. I don't know why I put in a smushed mooring, but I just easily grabbed that picture. And I even work with ecologists who are interested in understanding how these changes are related to polar bear migrations or where they're living. And we do use seals, or we have had projects where we've used seals to get ocean temperatures. Because when I started this as a grad student, we didn't even know if there was warm water around Greenland. And so these seals gave us a lot of information. They have these, you can put these loggers on the back that tell you temperature, salinity, and depth. And this little guy, they dive down, and then every time they surface is a blue dot here, and it satellite transmits the data to a satellite that we can download. And this is this glacier that I've been studying a lot. If we just look at how these 4 seals dove in 1 year around in this red box, we get a plot that shows this. So this is depth on the y-axis and month on the x. And we found that the warm water, this like 7-degree water, comes close to that fjord, but in the winter, which was not our original hypothesis. And that's paced by these like long, I guess, currents that bring this warm water towards this glacier that pacing is set by the oceanography dynamics. So this kind of led us to, okay, well, there is warm water in this area. Does it actually reach the front of the glacier, or is it blocked by some sill or some kind of wall a moraine that is in the water that might block, because all this warm water is at depth. And so if there was some kind of obstruction, that warm water would not get to the front of the glacier. So our next question was trying to map these long fjords. We initially did it with this Greenlandic fisherman, Akalu, and we're on his boat with our kind of fancy oceanography equipment. But Akalu speaks Greenlandic, and we do not speak Greenlandic or Danish. And so on this boat for about 4 days, we were going up and down this fjord. And finally, I think actually after day 2, we got across, we would point to where we were going, but we couldn't communicate what our science questions were. We got it across that we were looking for shallow water, and Akalu took our map and just like circled the areas, because we should have asked him this right from the get-go, because he grew up long line fishing in this long fjord. And what we found is, so this is this fjord that Akalu took us up. Now we have moorings in there. They're measuring ocean temperature and have been for 10 years. But originally, we didn't know anything about how deep these fjords were, if this warm current could get to the front of the glacier. This is one of the biggest glaciers in Greenland, so we're particularly concerned with how it's changing. And if that warm water gets to the front, it can kind of eat away at that location, and that can cause rapid change. So that we answered the first question is that, is warm water there? Yes, the seals helped us inform us about that. Is it getting to the front? Seems like it, because there's nothing really blocking that warm water from getting there. And so now our questions are trying to like really put numbers on what's happening there. So here in the schematic, we have the glacier flowing from left to right. At the front of it is the really interesting part. We want to know what's happening underneath the glacier here, and also at the front of the glacier here, to see how important that ocean is. But this glacier is also covered with a lot of sea ice and icebergs, to give you a sense of, and we can't measure those things. We can't give you a sense of how dynamic this glacier is. It is about 6 kilometers. I should know how much that is in miles. Hopefully somebody can do some quick math. But it's 6 kilometers across. This calving event is probably about 1.5 miles long and 1,000 meters deep. So we're trying to understand, when a big iceberg like this one breaks off, does that impact how fast the glacier is moving upstream in an impactful way, that it's moving more ice to the ocean and causing sea level rise? Or is it just these calving events just part of the kind of normal state of the glacier? Is this a new thing, or is it behaving the same as it always has? But it's very hard to measure. These things it's enormous. You can't put any instruments out here. This is all floating sea ice and icebergs here. This is grounded ice up here. And I just wanted to show this video to give you a sense of, first of all, it's beautiful and kind of awe-inspiring, but how kind of simultaneously fast and slow some of these systems are, which make them very hard to observe. A satellite might pass over once a day. You really need to have some instrumentation that, like, this is from a drone footage, some cameras, or something that's measuring this on a very kind of quick basis. I'm going to speed this along in the interest of time, but just a really sense of scale is insane. So we do put instruments out on this part of the ice. We put out GPS. This is another big calving event that took place here. We're trying to understand again, does the glacier calve more icebergs off, or speed up after a rainy day or a warm summer? What are the things that are driving this kind of variability of a glacier? And so these are GPS instruments that we put out in some kind of hairy situations. We now try to do more from the rock overlooking, because that's a lot cheaper and more effective and safer. We put out weather stations, but the surface lowers 2 meters in the summer every year, and so keeping those upright is challenging. We're trying to understand how water, when it's on the surface, so if a lot of these changes are driven by the atmosphere, we have more water on the surface, how does it get to the bottom of the glacier? Does that cause the glacier to speed up in a substantial way that would cause more sea level rise? So pretty much using any kind of instrumentation that we can. We now put out these fancy scanning devices that give us an image of the surface and the motion of the glacier every 30 minutes year round. So we're getting a much better sense of glacier behavior. And if we're kind of approaching, this stuff goes into models that kind of helps us know if we're approaching this kind of crazy high impact sea level curve. But there's a lot we don't know, particularly about what happens at this ice ocean interface, where the glacier ends and the ocean begins, and then what happens at the bottom of the glacier. And that dictates a lot of this response of how a glacier responds in a warming climate. And so this is just a picture of water kind of going through the surface of a glacier and entering a subglacial water system. So the last part that I wanted to take the last like 10 minutes to think about is, okay, well, why, how are we communicating this information, and why might it be helpful to engage in more conversations like this Lunch and Learn seminar? What can we actually do about it? The biggest predictor of our pathways are our future emissions. We've known that for a while. We still know that these are our emissions so far. If we don't have any policy and we're very fossil fuel driven, this is what, our CO2 in the atmosphere will look like with some, pretty severe emission reductions. We can limit that warming. And basically, there's no time that's too late to do any of this. We are locked into a certain amount of warming, but every moment that we don't try to do something better about it, we continue along the same path. So all of these paths are better than this path, and the biggest uncertainty, even with the uncertainty that we have in our models or in anything, the biggest uncertainty are the emissions. That's what drives the direction of all these pathways. And so I often get asked, like, what do we do about it? I mean, I think I don't have the silver bullet except to, be less dependent on fossil fuel emissions. And in order to do that, I think you guys showing up here is a testament to your interest in that. It's just, we have to keep talking about it, keep mentioning that this is an issue that I'm engaged in, and that it is impacting, what our heat waves look like and what our storms look like. It pervades every Earth system, and it's still very awkward or unnatural to talk about it. The challenge is that most people are, think it's happening and are worried about it. So this poll, this website is fantastic. It has like just many different drop downs, and you can see for different years, you can see, how people are thinking about, different aspects of climate change. But if you're just looking at Americans who think global warming is happening, yellow and up is above 50%. So most Americans think that global warming is happening. We're seeing it now. We're seeing it in fires and in floods and in hurricanes, and in, our ability to have healthy farms and all these different systems. And people are worried about it. So even if it's like a little bit blue, people are still, are thinking about it. The national average is 63%. So the biggest problem is not the people who don't think it's a problem. It's probably that we don't know what to do about it. And I say that for myself too, as I often, we can get overwhelmed by all the things and then feel like we don't know how to act. Part of that also is that we don't talk about it. So this is estimated percent of adults who discuss global warming occasionally or often with friends and family. So that's, pretty low everywhere. And we don't think it's going to hurt us personally. We have some people in areas that have wildfires or droughts or hurricanes who are like, yep, I'm feeling it. This is impacting me. But in general, we're not relating some of the hardships that we're experiencing now with the fact that these changes are due to climate changes. I find it very interesting that I guess I often think that the number of skeptics out there is greater than is reality. And so in this poll too, they do this every year of like, who is dismissive? And if somebody's dismissive about climate change, there's really not, those are the people that probably will not change their minds, and that your effort is not spent very useful in arguing with them about it. But most people are doubtful, have questions, think something's happening, but maybe it's not our fault, or don't understand some aspect of it. But a large, percentage of the American population is on the worried, cautious, concerned phase of things. And so those people want to know solutions, or want to know, that what they can do about it, or have some outlet to talk about it. These people, the disengaged and the doubtful, probably want a little more scientific explanation. But I feel like the science communication is, most people know what the parts that they want to know. We need to be a little bit more solution focused. And of course, there's no one the solutions come in many different ways. And I think that's great because we can kind of choose the ways that work for us. The biggest way, of course, is being less of a fossil fuel consuming economy. But we can present that in different ways by eating less meat or by having less plastic or driving less, and kind of acknowledging that those are all personal decisions. It doesn't just impact, that personal action, but impacts if you share, oh, I biked today, that gets the momentum for other people. So it's not just the action, but it's the communicating about the action that has the most impact. Climate is a threat multiplier of a lot of the things that we are worried about. These are just events in February where climate has played a heavy hand. A warm winter, floods, severe storm, a lot of the ways that we want to, help people in other countries, those are driven by climate inequities and access to kind of resources. And climate just multiplies a lot of those threats, a lot of those famines, a lot of those droughts, a lot of those insecurities in, geopolitics. So the church actually has, of course, as you know, has been a leader in many of these movements. The environmental issues are deeply connected with our values of stewardship and care for others. I think the church is a great place to have these conversations because people generally show up in good faith and give people the benefit of the doubt. They don't go to church looking for a fight, I don't think. They're interested in different perspectives, and having those you can have healthy conversations because this is your community. This is already your community. And the solutions are compatible with the things that we value, whether it's clean air or stewardship for the environment. And this was from the Pew Research Center, basically like looking at how religiously affiliated Americans link their beliefs to the environment. So they're not are not incompatible at all. And I think there's sometimes the perception that the church is anti and the environmental movement, when in reality they've been the leader in many of these efforts, and the solutions are very compatible with things that we deeply value. This article came out last week, which I think is fascinating. And I emailed the author for it over the weekend because I couldn't get it through pen. But most Christian American religious leaders silently believe in climate change, and informing their congregation can help open the dialogue. And so they found in their study that nearly 90% of Christian religious leaders believe that humans are causing climate change, with most believing human activity is a major contributor. Yet roughly half never discuss it with their congregation, and only a quarter have mentioned it more than once or twice. And in their paper, they say religious leaders shape the attitudes and beliefs of their congregations. Having a religious leader who talks about climate change predicts greater willingness to discuss it with fellow churchgoers and attend climate events. So I think what they're largely saying is that people think that their pastors aren't aligned with climate change, when in reality they are, and opening up that dialogue can really help. So there's a lot to be hopeful for too, and I'll end in a second, but really for the first time ever, the path towards renewables is, we can visualize it. Like, the renewable energy is cheaper than fossil fuel or coal energy. And a generation ago, we were hoping it would be, but we couldn't really visualize it. And now that technology is possible and is going to happen kind of independent of politics. It's just going to be a lot slower with politics in the way. People are interested in green technology. More people than ever understands the reasons to shift away from a fossil fuel economy and to reduce their consumption. And, everything we do now will impact the future. So that's all I have. I'm happy to take questions. Hopefully this gave you a little insight into my thinking about it. And I can, I guess, stop share and look at some questions, I think.
Thank you so much, Dr. Stearns. Are you looking at the questions actually?
I am not, but I can. So the first one, David, has any of your research been affected by DOGE contract cancellations I have two that were very focused on, thank you for that question, because that is hugely impactful, the research right now. And I have two grants that are specifically targeting inclusivity in climate science. Those were on Cruz's list of things to be canceled, but they have not been canceled yet. So yes and no. It's the threats and the uncertainty that, comes with the NASA changing their websites and changing their, reducing their websites, and NOAA reducing their ability to make their models. So TBD, not my day-to-day yet, but the uncertainty, it's hard to think of the future planning, and I have reduced the number of grad students I'm taking because of that uncertainty, and I'm not sure I'm going to get funding from these agencies. And I have been pushing my direction in more kind of USAID applied climate science, and now that is sadly shifting, and hopefully there are other ways that we can do that important work. Okay, this next one, I found it necessary to engage with paleoclimate studies as part of my research that Earth has been getting. You mentioned that this trend is not actually seen in much earlier. This points to a natural climatic cycle. So there is this natural pacing of our climate cycles. Could earlier events like the global ice ages have been triggered? No, so it was a little hard to tell in that long-term plot of that variability, but over time, our climate changes on really, like, it ramps up to warming and then it can cool quickly. So this is a great question. And right now, we've never seen the rate of change that we see now. So the natural pacing is much slower than what we see now. We could, if we did not have any human involvement, we would be entering towards an ice age in the next 30,000 years or something like that. We should be getting colder and approaching an ice age. And now I don't know if it was 30,000 or 40, my timing might be off, but we should be getting colder. The fact that we're not was the first evidence of, oh, we must be messing with this thermometer a bit. So really, yeah, really great question. I need to read it more slowly when it's done, and maybe I'll email you a response. And yes, your next question of how it, like, people first domesticated cereal crops during colder and wetter periods. It's all connected. And when we look at, like, the medieval warm period or the little ice age, and kind of art and religious kind of different avenues that come during these times of climate swings, they are, like, so intertwined with our history. I don't know, this development and spread of civilization, that's out of my wheelhouse. I think we're in a very tough spot now. I'm hopeful that the energy of prevailing heads will help us, and the fact that it's, like, right now it's cheaper and easier to shift to renewables. So I'm hoping that dominates the other forces that are pushing us towards a more kind of consequential conflict around fossil fuels. I'm not sure I answered any of your questions, but feel free to email me or follow up when we get through this last question, and then maybe we can go back to one of yours. Will this melting lead to higher salinity of the oceans? Will less ice on land masses lead to less water rivers? Great question. So then one of the reasons why the Arctic is so vulnerable is because of that. We're not creating as much sea ice in the winter, and we're melting more in the summer. And that pacing of sea ice really drives a lot of the climate. So it does make sea ice is just frozen ocean water, and it's fresh water. So in freezing the top layer as fresh water, the surrounding ocean is saltier, and that salt water is very dense. Salty water is denser than fresh water. And it plummets to the bottom of the ocean, and that's what drives our ocean conveyor. And you might have heard that in the news of, like, the Atlantic meridional overturning current, or like this engine that pumps our ocean current, is really dependent on the formation of sea ice. And so if the ocean in the Arctic becomes less salty, because not as much sea ice is formed, or because glaciers are melting and snow permafrost is melting, and that's adding more fresh water to the North Atlantic. That does impact. We've already seen it kind of slow down that current, and we know in the paleo record that that current has shut down in the past. So these questions of thresholds have been really uncomfortable for scientists because we know they exist in the past, but we can't say if it gets this fresh, it's definitely going to shut down. Having that exact metric has been very hard for modelers to say definitively. We know, like last time it was this warm, these ocean currents slowed down dramatically, and if it was a little bit warmer, they stopped. So we have that, but you know, Earth is different at each of these different climate periods, and so you know we have different distribution of vegetation and different things that are taking the carbon dioxide up. So it's that's been very hard. But another way to kind of convince people that the attribution to humans is really strong is that the legal world has taken this on. So now people are suing oil and gas companies because the evidence is so strong that you know, these emissions have caused this storm or this, like the likelihood of drought in this part of the world, and people are linking specific events to emissions, and those are gaining traction. So, you know, if there's enough scientific evidence for that legal framework, it's kind of a different world. Kathy's question, are there very popular level sources of good information you would recommend? Yes. Yeah, some of these government sites, hopefully they stay up. Like NOAA has a fantastic website that has some interactive things. So I can send Ruth a list of the ones that I pulled some of these visuals from. There's also some that have, you know, kind of common questions or skeptic myths about climate, and then a response. So I can send those along to, you know, help you think about different details a little bit differently. Yes, Jerry.
I just put my 2 cents in the chat. Basically,
Oh,
God's gift to the molecular cycles is the slow cooling of the planet to partially offset human greenhouse gas emissions.
that's right. So Milankovitch is the one who came up with our observations and theories of orbital cycles, and the fact that it should get cold. It is getting colder from these orbital cycles now. So if we were on another orbital pathway, we would have the natural warming and then our emissions on top of that, and we'd be, you know, just kind of increasing that problem. Another kind of direction that the climate world is going to, much to my chagrin, I'm trying to have an open mind, but I'm having a hard time, is kind of climate geoengineering. So, you know, we're on this path and it's bad. Are there ways that we can kind of artificially cool the planet from, you know, fertilizing the ocean, or and we know aerosols like volcano emissions cool the planet. So can we eject a bunch of, you know, sulfates into the atmosphere to cool it? That is terrifying to me, because it's kind of like we don't know, you know, we know a lot about our system, but we don't know enough, and they're going to be winners and losers of any of these decisions. Who's going to make the decisions of, okay, well, Bangladesh can get a little rainier if it means that Africa isn't getting as hot, or, you know, these are the laws around geoengineering for climate are not strong, and the climate impacts are big, and so people are coming up with a lot of options, and a lot of them seem very inequitable to me. And so having the conversations of, you know, it's not just an engineering solution. We can't engineer our way out of all of these things. We have to make choices that, you know, shift the balance now, not just put a Band-Aid on it, you know, later. And then if we stop, you know, artificially changing the climate, you know, there's a sudden warming that seems more catastrophic. So we're kind of locked. If we do choose those routes, we're kind of locked into some of them. So just kind of another thing you might see in the news kind of related to this space. Any other questions?
What's the consequence of the ocean currents slowing or stopping?
Yeah, hugely. So right now, our Gulf Stream brings warm water up the North Atlantic. And if you think of Maine and Spain, they're kind of like similar latitudes, but Spain is a lot warmer than Maine because that temperature is bringing, or that air is going over the warmer North Atlantic, absorbing a lot of heat and then bringing it to Europe. And so it would cool down Europe dramatically. That would be one of the consequences. And then the ocean is what distributes heat really across our planet. So it keeps our poles warmer than they should be just based on how much sunlight they get. And it keeps the equator from getting too hot. If that slows down, it's not transporting as much heat, and land and ocean at the equator maintains that heat, and the poles stay colder. So if it totally shuts down, that's very problematic. If it slows down, it's just not distributing as much heat, which a small change in temperature or precipitation are hugely impactful for the way that we live right now. So the inequities that come with climate change are huge. And we have rules about paying for climate losses in underdeveloped countries, but those are not always honored. And it's like cleaning up for a mess versus helping prevent it in the first place. And that's hugely impactful to people living through it.
Well, thank you, Dr. Stearns. I don't see any other questions, and we're at about time. So this has been very informative.
I'd love for also, if there are ways that I can help, think of these conversations in the space that you guys are communicating. I'd love to be a resource for you all. I feel passionate about the fact that the church plays a big role in how we communicate, and that there's a lot of facts that we all agree on. And so it does not have to be a divisive issue. And that you guys are experts in that communication. And it's something that climate scientists can really learn a lot from, is how to engage in those conversations and provide you with the right resources. So
Wonderful.
thanks for all you do. Yeah.
Yeah, well, thank you
you.
so much. Again, I want to say that this is recorded. And so there was a lot of information, a lot of really helpful information that you may want to go back to and view again or share with other people. It probably will be on the Central Seminary YouTube site. I'm guessing that's where it is, but it will be also on this Buttrey page of the Central Seminary site. Also, while you're there, there are quite a few other video recordings from past events that relate to climate change and climate solutions and theological biblical aspects of it that you might check out, as well as upcoming events. And in you're talking about the importance of the role of faith leaders, Dr. Stearns. We're having a continuing education series online in the fall for faith leaders during the climate change, and then also a ministry conference. So for all of you, encourage you to look at that as well and get those on your calendars or shared with faith leaders that you know. Jerry, you have one more thing you want to say?
Are these slides shareable either as PPX or as PDF files?
Either way, I'm happy to share it either way. I'll send them to Ruth, and she can distribute as needed. Yeah.
That would be great. Thank you. Again, thank you so much, Dr. Stearns. We're so grateful for your time. And thanks to all of you for taking time.
Showing up. Yeah.
Yeah. And blessings on the rest of your day.
Thank you.